Hello, students. I wanted to make a joke here, and I didn't have a good one. We're talking about torque. So we defined this a bit in the notes. There's not a whole lot going on here. If we have an object, so let's do the example problem in the notes. We have a torque wrench. So here is a fastener, and then here is the wrench that is on it. And there's the wrench body. There's our wrench, and this wrench is going to slip at an appropriate level of torque. So what's happening is when you use a wrench is there's some radius here. Okay, and so we'll put that in. It's radius R. And then we apply some force to it. And maybe we apply that force at an angle or something. So I'm going to call this the perpendicular part. There has to be some angle in here, which we'll call phi. And the torque is this funny looking little t. It's the Greek tau, which is R cross F, which is R times F times sine of phi. So this is important that this dotted line is along R, and this angle here represents the angle made with it, with that dotted line. So the angle F would make with R. So here's our vector R. So that's the definition of torque. And it's all just about trying to figure out what these missing things are. Right? So the example in the notes, we have this torque wrench, and if our tau is 350 Newton meters, so I want to be careful. The units for this have to be a distance times a force. And that looks like work, but it's not. These are not work, because what it is that this R here is not a real distance that this thing moves. It's the radius. All right, this is along the lines of what is the angle? How do we measure this angle? Well, a radian is a meter per meter. So this is not energy. This is torque, and that just happens to be the units. It's Newton meters. So if R is 0.2 meters, then we'd like to find the minimum force that we can use to tighten or loosen this bolt. So we're trying to find this. What we have is from this formula, so our torque is 350 Newton meters is 0.2 meters times the force times sine of phi. And we're trying to minimize F, which means we're maximizing everything else. So this sine phi needs to be 1. The minimum force you need is when it's perpendicular. And so F here will be 350 Newton meters over 0.2 meters. Well, that's 1250, I think. No, not 1250, 1750. Anyway, 350 divided by 0.2 is 1750 newtons. Okay. So if we can't apply that force for some reason, like This is more than most people's body weight, certainly more than mine. Let's say you can only apply 550 meters. Or 550 newtons. Well, the other thing you can do is extend R. You can put a cheater bar on your wrench, and that's just a pipe you slide over the handle and makes it longer. So we can change the length of the wrench, let's say. So our torque is R times 550 newtons times sine of phi, but we can also make this be 1. So R here would be 350 newton meters over 550 newtons. 350 divided by 550 is 0.64 meters. That's the example. That's like the first example in the notes. I'm going to let y'all work on some of the other ones in there. Because I want to go on from this, right? This is defining essentially the rotational force. So what's going on is we're trying to rotate this object. Any bit of the force here, I'll draw it in black here, that's along the object, along the radius, that can't help it rotate. The only thing that can help it rotate is the part of it that's perpendicular to the radius. And so that's the bit that's going to cause the rotation. It's going to, if there's going to be a force applied, this will cause the change in the angular acceleration. So we need to solve forces, and we have Newton's second law normally, and we still have it. But now we have to deal with rotation stuff. So we're going to talk about equilibrium problems. And for equilibrium problems, what we have is our acceleration is 0 and our angular acceleration is 0. So this could be something moving at constant velocity or constant angular velocity. So it could be rotating. But if this is true, then the sum of the forces in the y direction is the sum of the forces in the x direction is the sum of the torque is 0. They're all 0. And so we want to solve problems like that. And so we give you a means of talking about, we'll give you a list of directions to follow to go along with this. So we want to do an example problem here, and I'm trying to find a good one in these notes. Actually, we do these in the notes. So let me pause the video and see if I can't make this work to do what I want it to do.